Hello everyone. So in lecture 5 material, we saw that how we can use the concept of thermal radiation for heat transfer between objects. We saw the concept of black body and gray body, and we also saw how we can actually use different governing equations to calculate the heat transfer, thermal radiation heat transfer. Okay. So now let's actually have a look at an example to try to understand these concepts. Um, so let's say you have a 20 centimeter spherical ball that is at 800 Kelvin temperature suspended in air, as is shown in the figure here. And the ball has a diameter of 20 centimeter. And if you assume or if you approximate this body or this ball as a black body, so you need to calculate what is the total emissive power or the radiation emission from this body. What is the total amount of heat radiated within 5 minutes, and finally, what is the emissive power at a certain wavelength of 3 micrometer. Okay, so let's look at this solution of this example. So from the lecture, you should know by now that the total emissive power or the emission flux that is for a black body can be given by Stephen-Boltzmann law. And Stephen-Boltzmann law that states that EB, that is equal to sigma t to the power 4, can give us this emissive flux, and this is equal to also Q dot. Okay, so it means that it is the heat transfer flux as well. If you put the values of these parameters here, so we know sigma is the Boltzmann constant, and the value is a constant. So in exam you will be given this value. Okay, so you don't need to memorize this value. And then we know the surface temperature of the object, that is 800 Kelvin. So if you just simplify the units, Kelvin will cancel out, and then you will have to EB, that is equal to 23.2 kilowatt per meter square. And if you look at these units, you can see that this is a unit of flux. Okay, energy per unit meter square. Okay, and if we now look at part 2, so in part 2 we are asked to calculate the amount of energy, okay, that is radiated from this from this ball in 5 minutes. So we know from our basic understanding of thermal radiation that Q radiation, that is the flux of radiation emitted from a ball, is equal to sigma t to t to the power 4, as we saw in the previous slide. And if we look at it in terms of the amount of radiation, not as the flux of radiation, so we can calculate the amount of radiation from this flux of radiation by multiplying it by area. So the flux, because flux has area in the denominator, so we have to multiply it with the area. And if we multiply it with the time, the delta time, we can calculate what would be the energy or the amount will be emitted in 5 minutes. Okay, so this is exactly what we did here. So first we need to calculate the surface area of the ball. So that the surface area of the ball is 4 pi r square. Okay, and if you write it in the form of diameter, so it will be pi d square. Okay, so we know the diameter of the ball, that is it was 20 centimeters, so we need to convert it into meter, so it will be 0.2 meter. Okay, and if you take the square of it, the area would be 0.1257 square meter. In terms of time, we have a time of 5 minutes, so we need to calculate it into SI units of second. So we have 5 minutes times 60 over, so 1 minute has 60 seconds, so we can calculate it and we get 300 seconds. Okay. Now for the amount of radiation, we need to use this formulation, for example, here. So EB, we already know. We already know the area now, the surface area and the time. So if you put the values of these parameters, we can get this equation here. And finally, we need to also include a unit conversion, because, for example, here we have kilowatt, and we know that 1 kilowatt is equal to 1 joule per second. Okay, so that is the energy per unit second, and we are converting power into thermal energy. Okay, if you do this conversion here, So we can cancel out 1 kilowatt with 1 kilowatt. We can cancel out meter square with meter square, second with second, and then we only left with the kilojoule, that is the amount of energy. Okay, so we have Q radiation will be emitting 875 kilojoules. Okay, so just to put into perspective what this value or this number mean, if you try to visualize it, so it means that if you have 20 kilograms of water and you want to raise its temperature from 0 to 100 degrees centigrade, you would require this amount of energy. So you can see that this amount of energy is quite significant, and it is just coming out of a small ball of 20 centimeter. Okay. Now for the third part, we are to calculate the black body emissive power. Okay, so that is again EB, but now we need to calculate it at a certain wavelength. Okay, so if you look at this part here, for example, here this EB is the total emissive power irrespective of the wavelength. Okay, so we are not considering what is the wavelength of the energy or the radiation that is coming out in this total EB. But for part 3, we need to calculate what is the emissive power for a specific wavelength of 3 micrometer. So to do that, we have to use Planck's distribution law, okay, as we discussed in the lecture. And this is the formulation. You don't need to memorize this formulation. If this question is asked to you, this formulation should be given to you. So EB lambda, and it means that the energy, emissive power coming out of an object at a certain wavelength. So we know the values of C1 and C2 because they are constants. So we just need to plug the values from literature or from your notes, I mean. And then we need to put the value of lambda, that is the wavelength, that is 3 micrometer. Okay. And if you do the calculation, you will get the energy for this specific wavelength will be 3846 watt per meter square times micrometer. So it means that this is the unit of flux. So this is flux times micrometer, that is the wavelength of the energy, okay, or the wavelength of the radiation. So that is all for this part. Thank you for your time.